Next up is derivatives of trig functions. And again, this is something that you're probably just going to want to memorize, but we're going to do a couple proofs as well. All right, so you know where these come from. All right, let's do this. So the derivative of arc sine of u is du over dx, du over dx over the square root of 1 minus u squared. Look familiar? A little bit. You can also call this u prime over the square root of 1 minus u squared. Okay. The derivative of arctan is du dx, du over dx over u squared plus 1, or in other words, u prime over u squared plus 1. The derivative of arcsecant of u is du dx over the absolute value of u times the square root of u squared minus 1, or u prime over the absolute value of u times the square root of u squared minus 1. All right, now let's talk about cosine, arc cotangent, and cosecant, sorry. So the derivative of arc cosine of u is arc sine of u, but negative. So it's negative du dx over the square root of 1 minus u squared, which is also negative u prime over the square root of 1 minus u squared. All right, the derivative of arc cotangent of u, same, is negative du dx over u squared plus 1, or negative u prime over u squared plus 1. And then lastly, what do you think happens with arc cosecant? It's the negative ratio of arc secant. So negative du dx over the absolute value of u times the square root of u squared minus 1, or negative u prime over the absolute value of u times the square root of u squared minus 1. Whoop-de-whoop. All right, let's do some proving. Okay, first off, we're going to prove that the derivative of arc sine of u. Okay, so we're going to let y equal the arc sine of u, and we need to change the form. So we're going to say that the sine of u, the sine of y is equal to u. Remember, this is your ratio and your angle. Okay, so now my angle is y, so I'm going to draw my little triangle. My angle is y, my ratio is u over 1. Okay, so what I want to do now is, well, I would know from this triangle that the cosine, because we've done this before, the cosine of y would be the square root of 1 minus u squared. All right, so let us find if sine y is equal to u, okay, then we want to find the derivative, right, of basically what, of this ratio, so dx. Okay, so what we end up with is the derivative of sine y is cosine y dy dx, because of implicit differentiation. And the derivative of u is 1 du dx. All right, we're almost there. So we have, we need to gather we need to isolate dy dx. So I'm going to divide both sides by cosine y. So I get dy dx is equal to du dx over cosine y. And what is cosine y again? Oh yeah, remember cosine y is just 1 over u squared, the square root of 1 over u squared. So dy dx is equal to du over dx over the square root of 1 minus u squared, or that's, yeah, or 1 over the square root of 1 minus u squared times du dx. So same. Okay, you can split the fraction like that. All right, so let's prove tangent now. Okay, so we're going to start with y. We're going to let y equal the tangent, oh, sorry, the arctan of u. So we'll just rewrite that in another form, which is the tangent of y is equal to u. Remember, this is your ratio and your angle. So we set up our triangle so we can set the lengths of each side. Okay, so my angle is y, tangent ratio is u over 1. So let's go ahead and solve for the third side. I get, well, the square root of u squared plus 1 squared is equal to the hypotenuse. All right, so I like this form a lot better than this one. So let's just take the tangent of u. Tangent of y is equal to u. So I am going to take the derivative of both sides. And I get, okay, the derivative of tangent is secant squared y times dy dx. Okay. And that's equal to du. The derivative of du is 1. So du dx. Okay. So isolate dy dx. Dy dx is equal to du dx over secant squared y. And so then I just go up here, I look at what is secant squared y, the secant of y, basically. And I see that the secant of y is equal to 1 over cosine y, right? Which is the hypotenuse, u squared, the square root of u squared plus 1 over 1. Okay, so hypotenuse over the x value. All right, so I get this is equal to dy dx. Dy dx is equal to the derivative of u over the square root of u squared plus 1. And that's squared because it's secant squared. Okay, so simplified to du dx is equal to u squared plus 1. And that's how we get the antiderivative, that's how we get the derivative of the arctan of y. Excuse me, the arctan of u. Okay. All right, last one. We're going to do the arcsecant of u. Okay. And we're going to let that equal y. So again, the idea is we need to change the form. So I know that the secant of y is equal to u. So those are basically the same thing, just written in different forms, right? All right, so we're going to do y, and then the secant would be hypotenuse over the x value because it's the derivative or the reciprocal of cosine. So I'm going to have u over 1. All right, so solving for my third side, I got u squared minus 1. The hypotenuse. Okay, minus 1. Okay, so next up, I'm going to take the derivative of both sides. So I get the derivative of secant is secant tangent. So secant of y times tangent of y, and then don't forget to multiply by the chain, so dy dx, and that is equal to, what do you know, du dx, okay? So isolate dy dx to give me du dx all over secant y times tangent y, and I am going to make this a little bit easier on myself. I'm going to write this as du dx times 1 over secant y times 1 over tangent y, which is equal to du dx times cosine of y times cotangent of y. And that, I just feel like those are easier than looking at the reciprocated form. Okay, so cosine y would be 1 over u. Okay. So dy dx, and I'm going to write the du at the end, is 1 over the absolute value of u. Okay, absolute value because the hypotenuse is always positive. Okay, and then absolute value always a positive. Okay. All right. So next up, we have the cotangent of y. Going back to my triangle, cotangent would be 1 over the vertical. So this 1 over the square root of u squared minus 1. So times 1 over the square root of u squared minus 1 times du dx. Look familiar? Mm-hmm. All right, so that's how we get each one of those derivatives. You can always prove it to yourself, but really, I would memorize these rules, okay? All right, let's do some examples, and then we'll be done for today. All right, so the derivative of arc sine of 2x. So I'm just going to write on the side that my u value is 2x, okay? So I remember that from my rules that arc sine of u is equal to 1 over 1 minus u squared times du dx. So my u is 2x, so I'm just going to substitute this in. 1 over the square root of 1 minus 2x squared times the derivative du dx is equal to 2 times 2. All right, so I get 2 over the square root of 1 minus 4x squared. Number 2, arctan. So my u is equal to 3x, and I know that arctan is, the rule is 1 over u squared plus 1 times du dx. So arctan is just 1 over, and instead of u, I'm going to replace it with 3x, so 3x squared plus 1 times the derivative du dx is equal to 3. So times 3. So I end up with 3 over 9x squared plus 1. All right, number 3. Derivative of arc cosine of root x. So I'm going to make u equal to x to the 1/2 power. Okay, and then I remember that the derivative of arc cosine is the same as arc sine except negative. So it's negative 1 over the square root of 1 minus u squared times du dx. Okay, so here we go. I get negative 1 over the square root of 1 minus x to the 1/2 squared times the derivative du dx of u would be 1/2 x to the negative 1/2 So times 1/2 x to the -1/2. So I can rewrite that as -1. I'm going to move the x to the bottom. So 2 times the square root of x times 1 minus x. Okay. Last quick example, then we'll do a longer one. Okay, so we have the derivative of arc secant of e to the 2x. Yeah, I said that right. Okay, so u is equal to e to the 2x. I'm going to just take the derivative because I know we're going to have to. Okay, e to the 2x is e to the 2x times 2 for the chain. All right, so I remember that 1 over the derivative of arc secant of u is 1 over the absolute value of u times the square root of u squared minus 1 times du dx. Okay, so I get 1 over u is e to the 2x times, and that's already, I'll put absolute value, okay? And although e to the 2x would be positive no matter what x values you plug in, since the domain of e to the x is y is greater than 0. Okay, sorry, the range is y is greater than 0. Okay, so I get 1 over e to the absolute value of e to the 2x times the square root of e to the 2x squared minus 1 times du dx is 2 e to the 2x. So I notice that these e to the 2x's are going to cancel, leaving me with 2 over the square root of e to the 4x, because I multiply those two exponents, okay, minus 1. All right, here's a longer one. We have, where are the points of inflection? So we're going to solve this by hand, and then we're going to use a little calculator action, okay? So we're going to solve this by hand as much as I can, and then I'm going to use a calculator, basically, okay? So we have y is equal to the arc tan of x all squared. All right, so we're doing points of inflection. So this already tells me that we're going to take the second derivative, okay? We need to find the critical numbers and then test to see where the signs change to figure out our concavity, okay? And yeah, let's do it. So let's take the first derivative. So I have y prime, the derivative of arc tan is 1 over u squared plus 1 times du dx, okay? So I have a chain rule situation here. The squared is on the outside, the arc tan is the next inside, and then technically the x is the third inside, okay? So we're going to start with the outside. We need to take care of the squared. We're going to bring it to the front. So we have 2. Everything on the inside stays the same. So the arc, oh, I spelled that wrong. Arc tan of x to the first power now, okay, times the derivative of arc tan would be 1 over, my u is x, so x squared plus 1. And then du dx would be just 1, so I don't need to worry about that. Okay. All right, time to take the second derivative. Actually, let's combine these together. So I get y prime is equal to 2 arc tan of x all over x squared plus 1. That's not very pretty today. Okay, so let's go ahead and take the second derivative now. So y double prime is equal to, and I'm going to quotient rule this. Remember, it's low d high, high d low. Okay, so my low is x squared plus 1. So I'll go ahead and just rewrite that. X squared plus 1. The derivative of the numerator would be 2 times 1 over x squared plus 1 minus pi 2 times arctan of x times the derivative of the denominator, so 2x. And then the derivative of 1 is 0, all over x squared plus 1 squared. All right, we can combine some stuff here. I see right now that these x squared plus 1s cancel. That's pretty lovely. And then maybe we'll just rewrite this. So this is 2 minus 2 times 2x would be 4x times the arctan of x all over x squared plus 1 squared. All right, this looks horrible, but it's not so bad. Okay, let's find our critical numbers. So right now, is there anything that I can plug into the denominator to give me 0? So in other words, how could I make this x squared? I definitely just pointed at my iPad with my finger, and you can't see that. Okay, so this x squared, how can I make it into a -1? I can't, so there's nothing that makes the denominator undefined, or makes the denominator 0, which would give me a fraction of undefined. So let's just plug in a 0 for y and find our critical numbers that are zeros. Okay, remember the denominator will cancel. So I get 0 is equal to 2 minus 4x times the arctan of x, and this is where I used my calculator. I plugged it in on the graph, and I get a graph. Oh, I can actually show you. Now I can show you. Give me a second. Okay, so I plugged this in. This is definitely an equation that we cannot solve by hand. So we graph this, and I wanted to get my zeros, so I used my second calc feature, and I go ahead and use the 0 feature. So left bound, right bound. So left of the 0, right of the 0, guess, enter. The 0 is x is equal to -0.765 ... Okay, and then let's go ahead and find the right 0. So left bound, left of the 0, right of the 0, guess, and I see that this is symmetrical, so we also have a 0 at plus and minus 0.765. So I wrote that on my paper. Okay, so plus and minus 0.765. So now that I have my zeros, it's time to build myself a number line. Okay, so I have my number line with negative 0.765 and positive 0.765, and this is the y double prime number line. So I am going to use my calculator, and I'm going to use y double prime of -1, y double prime of 0, and y double prime of 1. Okay, we're going back to the calculator. Here we go. So I have second table, and I want to change my table set to ask because I'm just that type of person. Okay, so -1, and I see the output is negative, 0, it's positive, and 1, negative. Okay, so I get a negative, a positive, and a negative. So on my number line, so the graph of y is concave down, concave up, and concave down. So because the graph changes concavity at each one of these points of inflection, or each one of these zeros on my second derivative, then we have points of inflection at negative, we have points of inflection at x is equal to plus or minus 0.765, because y double prime is equal to 0, and y double prime changes signs. Oops. At x is equal to plus or minus 0.765. And that is it for today. Thank you. Sorry it was long.